Hello everyone, I would like to present you my progress on machine learning project dedicated to detecting melanoma cancer using deep neural networks. So, I would like to repeat some information from my previous presentation. The melanoma cancers overall correspond only to 5% of general cancer number. But when we take into account only skin cancers, the melanoma cancer corresponds to almost 75% of all cancer deaths. More than 10,000 people die annually in the USA, and it's only in the United States. It's a very deadly cancer if it is not detected and treated on early stages. You can get more information on statistics using the link below. The survival rate is strongly related to the stage on which the cancer was detected. The estimated 5-year survival rate for melanoma is more than 99% if detected on earlier stages, and it drops to 14% if it is detected in the latest stages. As you can see, the survival rate on first, second, and third stage is very high for both genders, as well as on unknown stage. But take a look at the survival rate on the fourth stage. It drops significantly, almost half of the survival rate on the first stage. You can get more information about these statistics using the link below. So, the main stages that were faced on these projects are looking for data source and loading images data, resizing all images, dealing with problems of different image sources, picking an architecture for future work, and training the model. As I said in my previous presentation, the selected data source is International Skin Imaging Collaboration, or ISIC. They provide an API to load images one by one from their gallery. The resulting dataset size is nearly 33 gigabytes, without 2000 of very high-resolution images, which is nearly 20-25 megabytes each. Metadata for each image is loaded separately as JSON file, and they should be merged into CSV or other suitable format. You can get more information about ISIC archive using the link below. The initial proposed image size was 224 by 224 pixels with 3 RGB channels, but actually images came in a variety of different resolutions. The precise number is 127 different resolutions. The image resolution varied from small one to very big one. All these images should be resized to be processed by network as an input. In addition, there are networks that are adaptive to input image size, but they won't be considered for now. But if everyone has proposals, then please feel free to write me. I want this project to be as successful as it can be. Image resolutions were divided into 6 different clusters. I have computed for each cluster and each resolution the result of division by proposed size of 224 by 224 pixels. After that, I computed average of each cluster, and it was enough to state that everything should be fine if I will just rescale images into proposed size. And after resizing, I took a glance at the images, and everything still seemed fine. But there was still a huge problem. Looking at these images, you can say what's wrong with them. A huge amount of images is covered by a marker. This can cause the network to train on markers, which we don't want to. The amount of images from this dataset is nearly 9,000. So, since we can afford cropping images by hand and use specialized platforms for now, the images would be cropped relative to the center, since almost all moles are in the center of the image. And actually, sometimes the results are pretty awesome, as you can see on these images. And sometimes they are not. At present stage, it is not possible to filter images by hand or recrop them, so the worst-case images would be temporarily removed from the resulting dataset. At most, 1,800 images were removed from the resulting dataset. Total size comparison is from 93 GB to 85 MB. The used architecture for now is MobileNet second version due to a number of factors. Since this network would be used in a real-world application, it will be a simple mobile MVP for now, and the network would be ported into a mobile phone. The MobileNet is a winner due to several reasons. First of all, this network is very lightweight. It has nearly 3 million parameters in basic view, but I will add my custom layers at the end of the network since I would be using transfer learning for this task. It has good description and examples over the internet, and the proposed network would be compared with other solutions, which will help to evaluate final solution. You can read about this network by clicking the bottom link, and I would recommend everyone to take a look at it. Accuracy metric was used in various papers and researches about mole melanoma detection. For now, the main metric will be accuracy, since it is pretty well suited for batch metrics. But future step is to implement F1 and AUK metrics for epoch-based metrics, since accuracy is not always a fair metric when you have an unbalanced dataset. Training networks on 25 epochs with all available data in batches resulted on the results you can see below. So you can see that MobileNet is a lot more lightweight than the basic CNN. This CNN was built with 3 convolutional layers, 1 max pool layer and 1 dense layer, and a resulting layer which was giving the output prediction. As you can see, the CNN has a lot more number of parameters and much bigger weight, and the accuracy of the CNN was less. So, to improve the MobileNet model accuracy, I would suggest to use more data augmentation techniques, because for now I'm using only horizontal and vertical flipping and small degree of rotations. Also, as I stated earlier, I want to implement F1 and AUK or other related metrics for each epoch or the model overall. I would also like to play with the model architecture, I mean the trainable layers that are added at the end of the trained MobileNet, to learn more complex features. And two final visions from me would be to load the missing high-resolution images, resize them and add them to the training and testing datasets, and to research more about other possible solutions. But pretty big part of changes and improvements in this network were based on previous related work. If you have any questions or suggestions, feel free to write me on my academic email box. And thank you for your attention.